Hello, y'all. This is Darrell Lee Berry Jr. back with some linear algebra. I'll be doing some problem walkthroughs in preparation for my exam today. I'll probably be getting asked some questions by some people, but I won't be streaming their voice, just me. And I'll get ready for this 8 I'll make in a little bit. So I'll be starting in a bit. I'll hold on for a few to join, and I'll start at the top of the hour or a little bit after that. And I shall adjust the crop a little bit. Hmm. I think that looks pretty much okay. I'll adjust it a little bit. All right, it's okay. Maybe I'll save off the edges a little bit. All right, there we go. So I'll give it a few more minutes and I'll go ahead and get started. And keep in mind I offer tutoring. You can check the website linked either through PayPal or um, Patreon, and science, math, a little bit of chemistry. So right now I have two associate degrees, one in science and one in arts, working on my bachelor's, which I shall have within a year. I'll be going to graduate school. All right, let's go ahead and get started. So I'll be going through 6 problems, and if somebody joins the stream and you have any questions, I'll be asking for that as well. And I believe the volume should be working fine. I checked that earlier, but if something does happen with the volume, I'll be checking the stream chat, so let me know, and we'll get that worked out as well. All right. All right, so problem 1 is going to be uh, finding the, you could say, the linear algebra representation of integral or differentiation transformation. So let's say if we took a derivative, it would take something in, let's say, third degree polynomial and make it a second degree polynomial. So the idea is going to be finding this matrix that does this, that maps a third degree polynomial to a second degree polynomial. So what we can do is, first thing we have to do is form a basis for the polynomials that we'll be using. So I'll say the basis for P3, we'll say we'll just have t squared with a 1, leaves t cubed, t squared, t, and 1. So that takes care of all of the different uh, aspects that we'll find in a third degree polynomial. And I could even, I'll say this is the bases, and we'll have a P2 basis, which equals T2, T, and 1. So with a second degree polynomial, we can have, up to 2 terms. So the first thing I need to do is find out what this transformation will need to do by looking at what a derivative does. So if I take a derivative of T3, that'll equal 3t squared. If I take a derivative of T2, that'll equal 2t. If I take a derivative of t, that'll equal 1. And if I take a derivative of 1, that'll equal 0. So if I was to write this in terms of the basis for a second degree polynomial, it'll be 3 times the first basis, 3 times t2, plus 0 times t, plus 0 times 1. And we do the same thing here. This would be 0 times t squared, plus 2 times t, plus 0 times 1. This will be 0 times t squared, plus 0 times t, plus 1 times 1. And this will be 0 times t squared, plus 0 times t, plus 0 times 1. So what I need to do here is put this into a matrix form. So the way it is here is actually at a transpose. So if I was to write it exactly how it is, it would be transpose D equals that transpose, which is 3, 0, 0, 0, 2, 0, 0, 0, 1, and 0, 0, 0 equals that transpose, so B equals 3, 0, 0, 0, 0, 2, 0, 0, and 0, 0, 1, 0. So that's our matrix that transforms a vector into that space. And that's easy enough. So what we can do at this point, the next step we'll do is, now that we have our matrix, next thing we'll do is show that it's a linear transformation. So a linear transformation has these two properties. So the first thing it needs to be is closed under scalar. So if I take a transformation of CF, it needs to equal the same thing as C times DF. And also, it needs to work under addition. So if I take the derivative of F plus G, it has to equal the same thing as the derivative of F plus the derivative of G. So what we can do is make a few generic vectors, or which in this case would be functions. So we can say F equals a x cubed plus b x squared plus c x plus d. And we can say g equals e y cubed plus fy squared plus g y plus h, right? So what we can do is we can go ahead and apply our formula. So f as a vector would be a, b, c, d, and g as a vector would be e, f, g, h. And this is important. This is why that vector was, when you take it directly from that, is it's orthogonal, because in order to make this work, you have to do d f or dg. So if this is a 4 by 1, this needs to be something by 4. In this case, it was 3 by 4. So that works. So you could always check the dimensions to make sure it works out. So if I have CF, to do the scalar one first, CF equals C, A, B, C, D. So that equals, oh, maybe I should pick a different symbol. I mean, technically it doesn't really matter. I just make that C squared. So it'll end up being CA, CB, C squared, CD. So if I were to multiply that by a, at least not multiply it, but take the function of that, it'll literally be the matrix that we have up here times the vector that we have here, just as we were showing earlier. So this would be 3 CA plus 2 CB plus C squared, right? and 0 just the last one just ends up being 0. It doesn't have any vector on it. So if I was to insert the P2 bases, what this means that we have 3CAT squared plus 2CBT plus C squared. And I can factor this out and say C, 3CAT squared plus 2BT plus C. And if I take just the transformation without the C, all we have to do is just delete the C. And we know from our matrix multiplication a moment ago that it will give us the same thing. 3A plus 2B plus C. And if I multiply that by C, we get C 3A plus C2B plus C squared, which is the same thing we got here when we did it uh, as a part of the problem. So that means it is closed under scalar. And now we could do the same thing under addition. And we can say D F plus G equals D. We're going to actually add these together. So it'll be literally all of this sum together. And we can actually simplify this a bit and say it'll be the transformation of, oh well, I use different letters for everything, so I guess it won't be. So what I'll do is, if I'm using random variables, I should have made the x and y something else, so I'll just make it z. So I'll say a plus e z cubed plus b plus f z squared plus c plus g z plus d plus h. So I remember in the actual proof to make sure to make the, make them both x squared. So now we can put this in matrix form. We can say f plus g equals a plus e, b plus f, c plus g, use cofactors to find the determinant for the matrix A, right? So it gives us this matrix, A equals 1, 3, 1, 0, 8, 4, 2, 3, 3. If I ever make a typo, let me know. Let's see, 1, 3, 1, 0, 8, 4, 2, 3, 3. And they want specifically the cofactor process. So one thing to keep in mind is that with cofactors, we're going to have signs on these. So this is plus and minus plus, and this is already plus minus plus. And it doesn't really matter how many you have. Like if we have a 4 matrix, then the next one would be negative and so on and so forth. But just the first one is always going to be a plus, and just put pluses and minuses all the way down the line there. And since we want to use cofactors, all we have to do is take one of the variables and put that on the outside, and then everything else we want to take a determinant of. So it'd be that determinant of 8, 4, 3, 3. And then this is a minus, so I'll go this way to make it, I'll show you two different ways. So that means it's going to be minus. There's a 3 there, and that should let me, I don't want to erase all that, but I want to put another box here, so let me erase some of that. So this is going to be a 3, because I'm doing that row, that, and since it's this row, I'm going to have to take everything else but that. So this is going to be determinant of 0, 4, 2, 3, because everything else is scratched out. I want to erase everything. And then we have one more, which is going to be the 1, which means everything else is scratched out. So it's going to be plus 1, that, and 0, 8, 2, 3. All right. So now all I have to do is get the determinants of those. So that's 1, and that's going to be 8 times 3 is 24, minus 4 times 3 is 12, minus 3 times, so remember the thing out in front, 0 times 3 is 0, minus 8, and plus 0 times 3 is 0, minus 16. So this is going to be 12 plus 24 minus 16. So that's 36 minus 16, so that's 20. So if you looked at the solution set, you know that I remember it being 20. So now let's do this a different way. So what I'm going to do is I'm going to write this one in blue so I can stay in the same spot. You can go along this thing in any direction. So I want to show it the harder way. But if you wanted to, you can take this thing and say 1. So that's still 1. An abbreviation for that is just drawing lines. So that's 8, 4, 3, 3. Minus 0. So I don't have to write anything there. And then plus 2. And this is going to scratch all of that out. So that's 3, 1, 8, 4. Now I did it that way because now I have one less thing to do. So that's going to be 24 minus 12 plus 2 times all of 12 minus 8. So that equals 24 minus 2 times 4. So that equals, I did some wrong math somewhere. What did I do? 12 minus, 12 plus, so I did wrong, plus 2 times 4. So that's 12 plus 8. So that also equals 20. So I showed you two ways to do it. One way is easier because there's a 0. So that's how you want to do it on the exam because there's less time. But you just have to remember to do your plus minuses because if this was a number here and I didn't do the minus, I would get the wrong answer. So if you write your pluses and minuses first, then you can do it in either direction, but just choose the one that's easier. Oh, I didn't write my 0 here. And then you'll still get the same answer. Any questions on that? That is correct. So if that was and we could actually do that part really fast. Make sure it's all clear. We'll do just that one part. So let's say this was, I'll call this B, and this was -3, then it'll be det of that would be, still be your 1, 8, 4, 3, 3. Then it'll be minus, there's a minus here, and it'll be -3 because a -3 is there, and then it'll be the same thing, 0, 2, 4, 3, because I scratch all of that out, and then we'll have to still do another +1 and do the rest. So that's exactly how that will work. And as you can see, I just basically just did it the same exact way. I know there's a minus there, and all you have to do is just remember to copy the whole number down, and it'll cancel out automatically without having to guess. All right, so that's that one. Any more questions on that? Right. So number 3. So now we're saying use Kramer's rule to solve this. And basically, the equation, and again, let me know if I have a typo. I have 4x1 plus x2 equals 7. And I have 3x1 minus 3x2 equals -6. So that's the matrix that we're going to solve to, at least that's the equations that we're going to put into a matrix to solve Kramer's rule to get what x1 and x2 is. So basically how we normally would do this is, which is a good place to start, we will put this in matrix form. And it'll look like that. And we know if we want to solve that, we could just do our row operations and everything. But what Kramer's rule says is, if you want to find what x1 is, or x2 is, I'll just call it xi, all you have to do is take the determinant of bi over the determinant of a, and I will give you the solution. So what bi is column I, we make that the v vector, and everything else we just leave to be the, so if I call this A in the matrix, and A1, and this A2 in the matrix, then we will still have our B, our A2, and so forth the same. Everything else is the same, but just the vector that we want the answer to, we let's say we want the answer to this one, then we just replace that row in the matrix with that vector, and then we solve. And this is going to be B. Right? So this is B. We want to find x1. We put it in the x1 position. If we want to find B2, then now A1 will be the same. And now we're going to put B in the B2 position. And then that'll go ahead and allow us to solve for x2. So that's the way this works. So all we need, any questions on that, by the way? Well, you don't put x1, you put b where you want to solve for. So let me be more explicit with this. So let's say we want to solve for, let's say we want to solve for x1. X1 is what we want to solve for, which is this term here. So now we're going to need b1. So I want to solve for x1, and x1 is going to be the left side of the matrix. I want to solve for that. So I'm going to take b1. I'm going to take b, I meant to say. This is b, because we always have that default thing, ax b equals b. So that's how I'm getting that's b. Ax equals b. All we're doing is just using that same uh, naming convention. All right. So I'm going to put my b here. And I'm putting my b here because in order to solve for x1, I need to solve for the first column. So I'm putting b in the first column. I don't need to solve for a2. So I'm going to put my a2 where it is. This is my a2 column. that's my B1. So now that's going to be 7, -6, because that's what B is. 1, -3, because that's my A2. Again, A2 is just the right column here. So now that's my B1 matrix. So when I take the determinant of B1, that's going to give me -21 minus -6. So that equals -21 plus 6. So that equals -15. I'll write my determinant of A, because we need determinant of A. Determinant of A, which is the original matrix there, that's still going to be 4, 1, 3, -3. So that's going to be, I don't need to actually write the A, determinant of A. So that's going to be -12 minus 3, which equals -15. So Kramer's rule says I want xi, so in this case I want x1, so that means that's going to be the determinant of b1 over the determinant of a, and I got my determinant of b1 here. It's going to be -15, my determinant of a here, -15, so that's how we got 1. So x1 is 1, and now I do the same thing. I want x2, so I need b2. So I know I'm going to have to put b where in the second one, because I labeled that A2. That's the second column. So I need to put B where A2 lives. So B is going to be here, 7, -6. And my first one remains the same. It remains what it is. So now I need the determinant of B2 to plug it into the equation. So that's going to equal -24 minus 21. That's going to be negative 36, -35, -45, -45. All right. So now Kramer's rule says if I want xi, I take det bi over det a. So I want x2. So that's going to be the det of b2 over det of a. I got my b2. That's -45. I have my det of a earlier. That's -15. So that's going to be 3. So x1 is 1, x2 is 3. And we can go ahead and test it, which, I mean, I think this is easy enough to test it the normal way how we used to doing it. I'll copy it down to save time. I have to delete a whole bunch of stuff. So now we have this, all of this here. Right? I'm going to have this here, and all I have to do is just solve the matrix here. So if I subtract row 1 minus row 2 and make that row 1, I'll get 4 minus 3, which is 1. I'll get 1 minus -3, which is 4. And I'll still have my 3 and -3. Then I will have 7 minus -6. So that's 7 plus 6. So that's 13. And this will still be -6. And then I can do row 2 minus 3, row 1, and let that be my row 2. So that's going to be 1, 4, 13. That's going to stay the same. So 3 minus 3 is 0. -3 minus 12 is going to be -15. And I'll use my calculator for that one. This is going to be row 2. So that's going to be -6 minus 3 times 13. So it's going to be -45. So if I divide this row by -15, that's going to give me 1, 4, 13. That stays the same. This is going to give me 0, 1, 3. And then if I subtract row 1 minus 4, row 2, and let that be my row 1, that's going to be 1 minus 0 is 0. So 4 minus 4 is 0. And 13 minus 12 is 1. And then 0, 1, 3. So as we see, x1 is 1, x2 equals 3, which is what we got over here. X1 is 1, x2 equals 3. So now we have confirmed that Cramer's rule works by doing it the normal way. So if you have time, I don't know what number he's going to give us on the exam, but if we have time, you could easily just do it the normal way and confirm that we get the same exact thing with Cramer's rule. Any questions on that one? It's correct. Well, I mean, you won't have to use cofactors to find the determinants, but that is one way. You can do the cofactor way. You can do the sort of basket weave way. Unless you tell us, I believe he said cofactor here just because he wanted us to show that we can do the cofactor. But if you're doing another problem, I mean, technically here I use the basket weave way. I just did the multiplication. So yeah, it doesn't really matter how you do it, but you are correct. If we had a B3, then if we had 3 rows and columns, then it would have to be B1, B2, B3. And it's just that BI, if it was B1, we would have our B here, which would be a 3 column, and then we'll still have A2 and A3 here, and then we would just do the same. Wait, sure, easy enough. So if, and I'll just use letters here, A, B, C, D, E, F, G, E, F, G, E, H. So this is my matrix. This is an A. So basket weave, all we have to do is go in a multiplication add on that way. So it'll be, and let me highlight these so it's a bit clearer. So we know that this is the diagonal, so it goes straight across. And we know that that is something, and this is the same thing. This is the same thing, and this that. So what I would have is AEH plus BFG plus CDE. So all I did was just take this diagonal, multiply it. I take this, then I run out of space, so I go here. So that's why that's DFG. And then I take this, run out of space, so then I go here, and that's why that's CDE. And then I got to do it the other way, subtracting. So then it'll be minus, and then I will go the reverse way. So it'll be CEG minus, I don't want to erase everything, just this one. And so this one would be BD, run out of space, H, minus BDH. And then it'll be the same thing for the last one. So it'll be minus, run out of space, FG. So minus AF should be E. So if I actually multiply that out with a 3 uh, tier matrix, it'll give you the same thing as if, matter of fact, I mean, I guess I don't know which one is the definition, but if you actually did it this way, like if you did A, and then that'll be times the determinant of E, F. Did I mix up my letters again? Well, it doesn't really matter. I might have just mixed up my letters, but it'll be like that. Like it'll be A times the determinant of that. If you multiply it out, you can actually see how this is when I do the first one, A times EH, right? And then if I do it the other way, it's minus A times EF. And what do you have here? Minus A times EF. You see it? So yeah, it's just a different way of coming up to the same thing. But I don't know why he wants us to do it a particular way, but maybe it's because we have to use the cofactor thing to do other stuff in this class, even though something doesn't come to mind exactly, but hey, all right, number 4. You're welcome. So this one says, so now we're getting our eigenvalues and eigenvectors. So again, if I make a typo, let me know. But I have A equals 1, 1, 5, 1. And we want to get the eigenvalues, eigenvectors, the first thing. So the first thing is that if we have, so we know we're used to seeing AX equals B. What an eigenvector does is it takes the uh, same vector and it scales it. So B, still call it B, but what it does is this matrix here will just take this same vector and just make it longer or shorter. That's why it's special and it's called an eigenvalue with an eigen. So what we need to do to solve for this is AX equals lambda IX, because if we want to sum matrices, it has to be with another matrix. So now this identity matrix makes this lambda matrix. So now we can sum them and subtract them. So AX minus lambda IX now equals 0 since I subtracted it from both sides. So I can factor this out and say A minus lambda I X equals 0. Now the way this works is, as we discussed earlier with the null space, X is going to be in the null space of A minus lambda I. And the way the null space works with the determinant is, if you take a determinant of something, if the determinant of anything, I'll just pick a different letter. If the determinant of F equals something other than 0, like if it equals 5, then the only thing that's going to be in the null space is 0. If the determinant of F is 5, then the null space of F is only going to be the 0 vector, which means we will never be able to solve any problems because everything will be a 0 vector. We would only get a 0 vector for everything. So what we have to do is we have to make the determinant of A minus lambda I equals 0 so that the null space of A minus lambda I, which is X, equals something other than just the 0 vector. Is that clear? Right? So that's why we do that. So I want to take the determinant of A minus lambda I, so that's 1 minus lambda, 1, 5, 1 minus lambda. And then we have what? 1 minus lambda, 1 minus lambda, minus 1 times 5 is 5. So that's going to give us 1 minus lambda plus lambda squared minus 5. So that gives us lambda squared minus 2 lambda minus 4. And this all equals 0, as we said earlier. So I can factor this easy enough. I can say lambda minus 4, no, minus 4, 1, no, 8, 2, 8. Oh, maybe not easy enough. I mean, 4 times 2 times 2. I need something that multiplies. Maybe I can't factor this. Something time, yeah, I can't factor this. All right, so we're gonna go to the trusty old lambda equals negative b plus or minus the square root of b squared minus 4ac over 2a. So that means that lambda equals negative, so the coefficients will be a, b, C. So we have negative negative 2. So that's 2 plus or minus square root of 2 squared. And it doesn't matter about the negative, it's just 4 minus 4 times, and C is negative 4 over 2 times A is 1, is just 2. So that equals 2 plus or minus the square root of 4 plus 16 over 2. So that equals 2 plus or minus square root of 20 over 2. So lambda 1 equals 2 plus square root of 20 over 2, which equals 2 plus square root of 4 times 5 over 2, which equals 2 plus 2 square root of 5 over 2, which equals 1 plus square root of 5. And this side will be lambda 2 equals, believe everything is the same, 1 minus square root of 5. Because basically I'll just have a negative here, and that's still that. That's still minus. Yeah, I believe that that will be exactly the same. If we make a typo, let me know. That seem good so far? Right? Awesome. So now we have our eigenvalues. So that was the first thing we had to do. Now for eigenvectors, we simply utilize the eigenvalues that we got. So where are we here? Oh, scroll too far. Oh, here we go. I just want to find this matrix here. Right? So we have this, and I'll make this a bit smaller. So I'll have to, there we go. I'll color this differently. There we go. So now we need to plug in our, uh, uh, so basically what we're going to do, we know that X is the null space. So we can set it equal to 0 because the null space means that that value makes the whole thing equal 0. So 1, this will be 1 minus this. So actually 1 minus 1 is 0. So that's square root of 5. And 1, 1. And that's still 1 minus that. So 1 minus 1 is 0. So that's square root of 5. And, we have 0, 0. And then we have over here the same 1 minus, so that's going to be negative square root of 5. 1, 1, negative square root of 5. All right, so now all we have to do is solve for x. And we know that x is, this whole thing is equal to 0. So what we can do is, well, we can take any, 1 is here. So we can say row 2 times square root of 5 minus that plus row 1. So basically row 1 minus square root of 5 row 2. So that means that that's going to zero out, but oh yeah. So basically what's going to happen is, let me actually write this out. So we have row 2 is 1 square root of 5, and I'm going to multiply this by square root of 5. So that's going to be square root of 5. And I'm going to multiply this by square root of 5. So that's going to be 5. So now I'm going to subtract this from row 1. So square root of 5 minus square root of 5 is 0, and 1 minus 5 is -4, and this is going to be still 1 and square root of 5 and 0, 0. So that's how that works. So that seems strange, but it works out. So then, yeah, certainly. So basically what I did was I wanted to simplify. In other words, you can roll reduce in any direction. I know normally we reduce the top row. But what I did this time, I left the bottom row stay the same. So if you can imagine, this is the same exact thing as if I were to swap my matrix and say 1 square root of 5, 0, square root of 5, 1, 0. And then if I was to say I'm going to subtract row 1 from row 2 from row 1, it will still give me the same thing, except it'll just have this at the top and this will be at the bottom. So it's the same process. So say it again. Oh, I messed up my. Oh, I see what you mean. I see what you mean. So what's going on is. Oh, I see what you mean. I miswrote. Thank you. I missed my typo. I appreciate it. So how did I do that? Oh, I did copy it down, but I didn't write it. Yes. So I knew a typo was going to come out at some point. Let me erase this whole thing. I was doing it with the wrong matrix. Let's do this again with the proper matrix there. And I know this is going to be. No wonder why it seems strange, the matrix, because I was missing the 5. Okay, there we go. Let's look at this again with the matrix proper. So this time I would say, why don't we divide uh, I'll multiply the top row by square root of 5 and then add it to the second row. So row 1, go ahead. Oh, that's right. Thanks. Appreciate it. I try to speed things around. I forgot to delete that. So row 1 times square root of 5, and it's actually going to be subtracted minus row 2. That's going to be row 2. So that's going to be row 2 minus uh, square root of 5, row 1. It's going to be my row 2. All right, so I'm going to write this out. So if I take row 1 and multiply it by square root of 5, I'll have 5 here, and I will have square root of 5 here. And I'm going to subtract that from row 2. It's going to be negative, negative. So my row 1 is going to stay the same, square root of 5, 1, 0. And now 5 minus 5 is 0. And square root of 5 minus square root of 5 is 0. All right, so we have that. So that does make more sense. It's like the other one did look strange. So now what I'm going to do is, I could just leave it like that actually. Like I say, square root of 5 x1 equals negative x2. So of course I'm going to times everything by the square root of 5. If I do the square root of 5 on both sides, it's going to give me x1 equals, okay, that didn't do what I expected it to do. Okay, well, that's going to just stay like that. It's going to be just complicated. So x1 is going to equal negative 1 over square root of 5 x2. So that's my x value. And okay, no, it's still going to be complicated. So I could just say x equals uh, negative 1 over square root of 5, uh, 1 x2. So I can say x equals, if I let x2 equals 1, negative 1 over square root of 5, 1. So that's my first eigenvector. Any questions on this process so far? Right? So then we can do the same thing on the other side. And the match should work the same way, except I don't have to subtract that. Let's see what the signs do differently. So I'll say row 2 minus square root of 5. I guess I should say plus square root of 5 row 1 equals row 2. So the square roots always trip me up. So let me actually multiply it out here. So we have row 1 times square root of 5. That's going to be negative 5 times square root of 5. That'll be square root of 5. We're going to add that to row 2. So this is still going to be negative square root of 5, 1, 0. And when I add negative 5 to that, that's 0. That's square root of 5 to that, 0, and 0. So that gives us what we were supposed to be looking for as well. So now we have x1 square root of 5 equals x2. And I'll bring it to the other side. So now x1 equals 1 over square root of 5 x2. So x equals 1 over square root of 5 1 x2. And we'll let x2 equals 1. x2 equals 1 over square root of 5 positive 1. And that's what that did to the sign. That's my eigenvector. So that's what they wanted us to find. So now we have, I also put it in the form professor liked it nice and neat. You can say the eigenspace spanned by the eigenvector 1 plus square root of 5 is spanned by the vector negative 1 over square root of 5, 1. And we can say the eigenspace of 1 minus square root of 5 is spanned by the eigenvector 1 over square root of 5, 1. Right. So that's the farthest we can go with getting eigenvalues and eigenvectors. So now it wants us to find the use what you found to write A equals that, the diagonalization of A. All right. So I always start here. A key equals uh what is that? Key diagonal. That just helps me remember it. So A equals P diagonal P inverse. And he wants us to find what goes on the other side. So when it says what is the diagonalization of A, right? The diagonalization of A, you want to find what's on the other side there. So what that stands for is T equals the vectors. So if I called my eigenvectors x1 and x2, T is x1, x2, which means T is going to be negative 1 over square root of 5, 1, 1 over square root of 5, 1. So that's my P. And P inverse is literally the inverse of that, but it's going to be 1 over the determinant of P. And to make this a inverse, you just take the negative and you swap these. So that's going to be 1 divided by, so determinant of this right here, that's going to be negative 1 over square root of 5 minus 1 over square root of 5. And I'm going to swap those. So that's 1 negative 1 over square root of 5. And then I'm going to make other one negative. So that's negative 1 and negative 1 over square root of 5. So that's T, and that's T that. Go ahead. That's the diagonal. So the diagonal equals capital lambda, they call that. So that's literally going to be lambda 1, 0, 0, lambda 2, which is going to be, where's my lambdas at? Let's copy this down. All right. So this is literally going to be this, this, 0, 0. So that's that. So in this case, and my understanding is it doesn't have to be the eigenvalues, but if you have a system that has eigenvalues and eigenvectors, then the diagonal will be the eigenvalues. That is, yes, it does. So, well, all you have to do is treat it the same as you do your P. So I put my P1 over here. So my lambda 1 is over here. I put my x2 over here. So my lambda 2 is over here. And all I did was just go up and get my, oh, switch my colors. Let's switch my colors. I went and got my x2 from there, which is on the right side, which is there. And that's my lambda 2. As you can see from here. And then the same thing. I get errands for lambda 1. So I know this was my first eigen vector, first eigenvalue with the negatives on it. So, oh, and I forgot my negative. Did I forget my negative? I think I swapped it. Did I switch? Oh, that's what I did. Oh my gosh. So I put the vectors. I meant to put the, what did I mix up? Yeah, I mixed something up. Oh, no, I didn't. I just, the fact that the negatives are different is throwing me off. So there's a negative on the eigenvector, uh, but it's positive on the eigenvalue. And here it's both positive, so that was throwing me off. At least I guess you could say it's negative here. Say it again. That's right. It lines up. Exactly. So, but yes. So you can see how every single one, everything that's orange is the one stuff. And the one stuff, the orange stuff is all on the left. And everything that's red is the two stuff. And the two stuff is all on the right. So that's all you have to do. And the way I do it, like if you see how I work my problems out, I just always work it the same way and put everything on the same side, and it works out that way. I'm just checking my negatives to make sure I wrote everything properly. Yeah, that's positive. Yeah, the negative thing was just throwing me off, but yes, everything is good. And that's it. So we got our diagonalization. So what this means is that so if I was to actually write the answer in completion, if you was to write this out, if you was to actually multiply this out, and you would put negative 1 over square root of 5, 1, uh, 1 over square root of 5, 1. So this is how you like literally write it to finish your answer. 1 plus square root of 5, 0, 0, 1 minus square root of 5 for the lambda. And then where's my P inverse right there? 1, negative 1 over square root of 5, and negative 1, negative 1 over square root of 5. Let me write this better. All right. So that's the actual answer. This is the diagonalization. So what this means is if we were to multiply all this out, even though it looks so ugly, if we were to multiply this out, it would give us the original A that we had, the 1151. It might be hard to see, but a lot of the uh, uh, and hold up, my pad froze. Let me share again momentarily. So sometimes this program, when it's uploading data, it freezes, like when it's uploading the backup thing. So give me one moment, sure. I just have to close the program and open it again. Right, it's working again. Share on the way. Right. All right, so that's it. So that's the answer to that. So you can see that's what it always does when it does that. Like the last thing it was uploading, it disappears. So I had corrected this to look better, and I corrected that. So what happened is, like, it might be hard to see, but a lot of these square root fives will be canceling. There's a lot of stuff will cancel, then the negatives will cancel, and you'll end up with the same thing that you had before. And it also asks for the last thing. It says use the decomposition of A to find each of the seven. So the way this works is if you want A to the n, it's going to be, all of this is going to be the same. I'll just copy it down, except the middle thing, the diagonal, you want to put in there. So if I wanted A to the 7, I would copy all of this down, except I would put a 7 exponential or exponent on each of these. And then when I multiply all of that out, it would actually give me a matrix that equals that matrix to the 7th power. It'd be the same thing as if we took A and multiplied it manually and got something. So then we'll have A squared and multiply by A again, and now we got A3. If we did that 6 times and we got A7, it'll give us the same thing as just multiplying these 3 things out. So that's what that's about. All right. Good. Any questions? Oh, that is correct. Yes. I forgot that part. Thanks for mentioning. Typos, what happened? So hold up. I'll just slide this over. Actually, I had it written there, but I forgot to copy it down, which I actually often do in real life. I'm going to have to remember that on the exam. So this will actually be, what would it be? -2 over square root of 5. So -2 over square root of 5. -2 over square root of 5. Yeah. And if we didn't have that there, then we wouldn't get the proper answer. It would be off by -2 over square root of 5. But if we just multiply that in, then it will give you the full matrix again in the proper value. That's very important. Thanks for catching that. So yes. So, but does not matter. You can, for instance, start with these two, and I've actually tried it. Like I've actually multiplied these two first. One thing about it is sometimes some matrices are easier to multiply. So I guess just as far as I know, you can't do this though. Like you can't like multiply the two on the outside. You can't do that. You have to do either these two and then do the third one, or these two and then do the third one. Maybe if you did this, you would have to like do a transpose or something. I don't know. But I've only did it these two together and then the third one, or these two together and then the third one, and then you can multiply this and at any point. So for instance, if we multiply this in early, we could get rid of those square roots of 5s. Or maybe it might be best to multiply it into here early, and then you can get rid of that square root of 5 there. Well, then we'll still have one in the denominator. So I don't know. I guess it's up to you to pick which one to be easier to start with. But as long as you don't cross over any one of them, it should be good. Good question. So what I'll do, give me like a minute. I'll take a restroom break momentarily, and I'll be right back. And maybe y'all can take a break too. Why don't we take a 5-minute break? Then I'll be back at like between 5 and 10 minutes, and then we'll do the last 2 problems, which are a bit longer. So I'll be back in 5 to 10. Sitting here, I'll just check some email and continue taking a little bit of break, and we'll start in a few more minutes. All right, how we doing? All right, how we doing? Is everybody back? We'll give it a few more minutes. Let people know, which we call them, know we're about to start on the last two problems. How you doing, Kevin? You back? How you doing, Michaela? Are you back? I can't hear you, Kevin. I see it saying talking, but is it my computer? Some. And I thought I saw Kevin talking, but I didn't hear him. By the way, I realized I made another algebra typo. This is 1 over that. So this was actually 1 over -2 square root of 5. So it actually becomes negative square root of 5 over 2, which now is more clearer how that stuff cancels out. Because, you multiply that in, the square root of 5 cancels out for 1, and so on and so forth. So you end up with 1 plus 1/2. It starts to all balance out. So, but if you want it, you could do the math later. I'm pretty sure he's going to give us easier numbers than this. I mean, I can't see getting numbers like this on the exam. So, but also let's go ahead and get started. That was about 10 minutes. So what we'll do is go to number 5 and number 6, and then we will be done. And we could actually do a famous rule as well, even though it's not on the practice exam. He did mention it a lot. But you can see at the end. So number 5, it says, uh, recall that for hold up, wrong screen. Let me see. Oh, okay. Matrix below Markov. Okay. We have the Markov chain describes the probability of a particle being in state A or state B. So suppose that the probability of the particle being in A, given it was in A, is 0.8, and the probability that the particle is in state B, given it was in A, is 0.2. And notice that they add up to 1. Uh, the probability that it moves to state B, and the other probabilities, the probability that is in A, given it was in B, is 0.4, and the probability that is in B, given it was in B, is 0.6. So basically, they just took this and made a matrix out of these probabilities. So basically, these are the probabilities of the particle changing states from one state to another. And we're going to use this relationship to determine things about the particle that they give us. So it says, I suppose initially the particle is in state A, given by the initial state equals 1, 0. So they say 1, 0 t, but means 1, 0. What is the probability that will be in state A after 1 second? So, and what about state B? So the way this works is this matrix gives us, and this is the transformation. So this is a linear, maybe, I don't know if it's linear or not, but it's a transformation. It has to be linear in algebra. Linear transformation that is a transformation for 1 second. This is a transformation. So we're given this vector, all we should have to do is say 0.8, 0.2, 0.4, 0.6, just like how we did the transformation with the determinant. We had our determinant and we just multiplied our function to it. It's like this is our matrix that does the transformation. This is the function that we're starting with. So we can say m f equals that, which equals 0.8 plus 0 uh, and, 0.2 plus 0. So that's our probabilities. And the way we set it up, we have probabilities A up here and B down there. So this will be the probability for A. This will be the probability for B. So the probability that is in A is 0.8, and the probability that is in B is 0.2. All right. Any questions? Pretty straightforward. Uh, it says find an expression for xk, the probability distribution for the particle after k seconds. Now, I did this slightly differently than the solution page, which is the way I understand it, and I got the right answer. So what we can do is we can actually use the fact that a k equals t diagonal p inverse that we got from earlier, and with this as a k. So we wanted to, but what you say? Yeah. So this was just the A part. He was asking, uh, uh, suppose that's our initial state. What's the probability after 1 second? This is our 1 second transformation. So I just applied the vector they gave me to the transformation, and that gave me, which is ironically exactly what they told us in the problem. I mean, they told us um, a particle being in state error B, suppose is in state A, it goes to A at a probability of 0.8. So, I mean, that's what they gave us that answer. So hopefully we do it like this. But it is nice to be able to show algebraically that it does give you the answer. So that's that. And now what we need to do is, I mean, one way to do it is to use the same process we did earlier, but we have to be more careful because we're going to actually have to calculate this one out to see what it is. So basically what this will end up being is x k, or the probability that we're looking for is this, right? So they gave us our a, which is m. So maybe it might even be more appropriate to say mk. And we know that we can find this out after so many seconds. So in other words, this is a transformation after 1 second. So we want 7 of these transformations. We want 7 of these transformations to happen to give us the answer that we want. So all we have to do is just do that calculation. So the first thing we'll do is take this matrix and find our eigenvalues, and it'll be the same exact process as before, except just with different numbers, harder numbers, but the process is the same. So I have a minus lambda I, determinant of that, equals determinant of 0.8 minus lambda, 0.4, 0.2, 0.6 minus lambda. So that equals 0.8 minus lambda, 0.6 minus lambda, minus 0.08. So that equals 0.48 minus 0.8 lambda minus 0.6 lambda plus lambda squared minus 0.08. Let me know if I make a typo anywhere. So then we have lambda squared minus 1.4 lambda, and then plus 0.4, and it all equals 0, because we're just still doing the same eigenvalue process. So you can put a det there to make it look familiar. So now we have to solve for this. And again, I don't think I'm able to, I guess you could do a squares thing, but I don't know how to do that. So lambda equals uh, negative b plus or minus square root of b squared minus 4ac all over 2a. So that equals, so that's a negative 1.4. So 1.4 plus or minus square root of 1.4 squared. So 1.4 squared equals 1.96 minus 4 times 1 times 0.4. So that's 1.6 all over 2 times 1. So that equals 1.4 plus or minus square root of, could be 0.3 0.36. 0.36 over 2. So that equals 1.4 plus or minus. I'll take the square root of that, and that's 0.6 over 2. So the numbers start to not look so bad as you get through it. So, I take the square root. So then we have lambda 1 equals 1.4 plus 0.6 over 2. So that equals 2 over 2 equals 1. So what do you know? And then lambda 2 equals 1.4 minus 0.6 over 2, which is what, 0.8? Yeah, 0.8 divided by 2, so that equals 0.4, so that equals 2 over 5. So you can see how the process, just the fact that it's given us, I mean, round enough fractions. I mean, it's not round numbers, but it's round fractions to keep us going. So that's okay. So now I have my eigenvalues. So now we can use this to get the eigenvectors. So take this same matrix. I'll try to remember everything I copied down this time. So we have 0.8 minus 1. So that's actually negative 0.2, 0.2, 0.4, and 0.6 minus 1. So that's negative 0.4. And you notice it gives us the proper configuration for a eigensystem because one row is going to zero out. And then we can make the other row negative. So it's going to be 0.2. If I make that positive, minus 0.40. Right? What I'll do is add these rows together, and that zeroes out. And I make that, I swap the negative, even though that was unnecessary, but I just had a habit of doing that, I guess. So x1, 0.2 equals 0.4 x2. So x1 equals 2x2. So that means that x equals, so when that's x1, x2, so that equals, if I make x1 equals 1, that's 1 plus 2, 1. Because if I make x2 1, there's a 1 there, and x1 is 2 times that. Let me know if you have any questions so far on the process and what we're doing. And I don't see anybody else. See anybody else come to the reading room? I don't think I saw anybody else. My other one. All right, so that's our first eigenvector. So now we're going to get the other one. So this one is going to be 0.8 minus 0.4. So yeah, I don't have to actually use the fraction. So 0.8 minus 0.4, that's 0.4, 0.4, 0.2, and 0.6 minus 0.4 is still 0.2, 0. So this was looking good as well. So I can subtract half of the top row from that one, and this will be 0.40, 0.40. So now that's going to be 0.4 x2 or x1 equals negative 0.4 x2. So that means that x1 equals negative x2. So x2 eigenvector equals same thing, x1, x2. So if I make x2 1, x2 is a 1, so x1 is going to be negative 1. So I have some very nice eigenvalues and eigenvectors here. So to remind myself of what they are, the eigenspace with 1 is spanned by 2, 1, and the eigenspace with 0.4 is spanned by negative 1, 1. And if you see a typo, let me know. So now all we have to do is remember that what we want is this matrix that's going to transform so many times. We're not going to worry about the 7 now. I'll just put a K there. Maybe I'll actually put an N because it's easier to write. And this is going to be P, that in P inverse. And we need to find that matrix because on the key, he actually put some answers there. I remember like he actually has some numbers. So if we get a problem like this, we're going to actually have to well, it's not going to be that bad because he wants it's a probability, so we'll be able to take a limit. But we're going to have to make sure we get that matrix right. So P, again, is going to be simply x1, x2. So P is easy enough. 2, 1, negative 1, 1. That's my P. My gamma or lambda n is going to be eigenvector 1, 0, 0, eigenvector 2, that whole thing to the n. So that's going to be, I wrote it there for convenience, 1, 0, 0, 0.4 to the n. And then P inverse is going to be 1 over determinant P. And then you swap these and make this into a negative. So there's going to be 1 over, so that's 2 minus negative 1. So that's 2 minus negative 1 plus 1. And then we have to swap these, so that's 1 and 2. And then we have to swap the sign, so that's negative 1 and 1. All right, so that means that mn equals 2, 1, negative 1, 1, 1, 0, 0.4, n, 1, 1, negative 1, 2. Okay, let me know if you have any questions or anything like that. Okay. Ah, yes, thanks. I should get that. I have to remember that. It's going to be the one thing I miss on the exam, I bet. But you are correct, yes. I have to add that there. So maybe now I keep forgetting this here and we reminded each other so I remember it on the exam. All right, so we got that. So now we have to do is just work this out. So what I'm going to do is I'm going to do this one first. So I'm just going to just work in that direction for no particular reason. So this is going to be 1 times 2 is 2, plus 0 is 0. And then 1 times 1 is 1, plus 0 is 0. And then we do the next one, 0 times 0 is 0, minus 0.4, and 0 times 0 is 0, plus 0.4. Oh, I forgot something. Crap. I forgot my ends. Let me back up. That would be the case if we didn't have ends. I mean, technically I didn't do the multiplication wrong, but it's just this will be 2 to the 1 n. So in other words, just let me just do it over since I forgot to do my n thing. It might be easier to just put the n there now. I have to remember to do that as well so I don't forget to multiply the n out. So let me start this again. So that's going to be actually, let me give myself a bit more space. This is going to be 2 times 1 to the n. So it's the same multiplication plus 0, but there's an n on that. Then there's going to be 1 to the n plus 0. And then the second one would still be the same, it'd be 0, but minus 0.4 to the n. And then it'll be 0 plus 0.4 to the n. So really it was all the same, except I just had to put that 1 in there because everything else is multiplied by 1. But again, if we don't have the in there, then we defeating the purpose of trying to solve to multiply this thing. So we want to be able to just add a 7 up in here to solve for that. And then I have to just carry this over 1, 1, negative 1, 2. And I'm just going to just save the 1/3 for last. Let's hope I don't forget it at the very end when I should do it. So now I have these. So that's going to be 1 times. Now let's stop for 1 second. Actually, I could just simplify this one moment. So the problem said that, well, I guess it doesn't really say, but we know that k is going to be greater than or equal to 1 because there's not negative seconds. So it's going to be 1 second or greater. And then they do say actually after k seconds. So we know k is going to be positive. So what we can do is we can go ahead and know that if I have 1 times a million, I mean, to the million power, it's still going to be 1, right? So actually, instead of actually writing the whole thing over, I'll just delete the 1 anyway, because that's going to be 1 to the infinite number of ones. That doesn't matter. And this is going to be 1 to the infinite number of ones. That doesn't matter. So that's still, we could have just actually kept it the same way it was at the first time, just adding into the second term. There we go. You got some detail on that anyway. So now I'll go ahead and multiply this second one, since the 1 is not going to do anything. And we're going to have 2 minus negative 0.4, so that's plus 0.4 to the n. And then it's going to be 1 minus 0.4 to the n. And then we're going to have 2 minus 2, 0.4 to the n. And then 1 plus 2, 0.4 to the n. Now that's 1, and then we just have 1/3 on the outside. Right? And that's really as far as we really need to go, technically. So, I mean, yeah, that'll give us that. So in other words, if we wanted into the 7, I don't know what problem I was thinking. Maybe I was thinking about a homework problem. He's not asking for 10 to the 7 here. But whatever n we put, if we want 7 seconds, we could just put 7 up in there, and it'll give us a new matrix, that to the 7. And then all we have to do is just multiply, for instance, our beginning state times all of this, and it'll give us the probability at 7 seconds. So this will give us however many seconds we want. And now it says, what is the long-term probability distribution of the particle after a long amount of time? What are the probabilities of a state A and B? Oh, and by the way, before I go to the third part, the final part for this problem, any questions so far? Good. So what this means is, all right, if a long amount of time goes by, that's like a whole lot of seconds. So I'm going to just say a million, like infinite seconds. So we're going to take the limit as n goes to infinity of mn, which equals the limit as n goes to infinity of this whole thing, which I'll just copy down so I don't make another typo. And I'm glad I did that because I would have forgot to write the 1/3 that time if I didn't copy it. I saw the 1/3 again when I copy it. So that's that. So we want the limit of that, right? So we know how to take limits. All we have to do is put an infinity for wherever the n is. So if I put an infinity on a fraction, what is that going to give me? 0. Yep. So it's going to be 2. It's going to be 1, 2, 1 times 1/3. So that's going to equal 2 over 3, 1 over 3, 2 over 3, 1 over 3. So the probability matrix for an infinite amount of time is that. And I know what I want to do if I want to take the, just like if I had the function df, Now it's going to be m infinity f. So it's going to be this times the f they gave us, which is 1, 0. So that means after an infinite amount of time, there's going to be a 2/3 probability in A and a 1/3 probability in B, which is how, I mean, I guess I can't say it's how the professor got the answer, but it is the answer professor had if you saw that the answer sheet. So that's how I got the answer. So on exam, this is how I'm going to do this one because I don't even know how he did it. I see what he did, and I'm sure that's in the book, but I never learned that. Whatever he did, I never learned it. So I'm going to do it this way. Any questions? And the good thing is we did the other problems this way, so it's kind of like a reinforcement of what we. He did have a 7. I don't remember which problem he asked for 7. I guess we just didn't calculate that when I was 4. That's going to be a lot of calculations. So, but as long as you know how to do it, and this is one where you know we had an infinite number of seconds, so you can see how it works out. The process is the same for the other one. I could have made a typo on the number or something somewhere and throw it off, but the process is right, and it's good. This one was able to get us to the end of the process. So you can see I did the same process as the last problem. You know the process works. And so for the last problem, that'll give us plenty of time to take a break for the exam. We have 6. And now he's saying let A be the symmetric matrix. Then let me know if I make a typo anywhere. 1, 3, 3, 1. And so first we want to find the diagonalization of A. Now, me myself, I'm often confused by this terminology and stuff. I always start with this AP equals P diagonal. So A equals P diagonal. This goes to the other side, P inverse. This is the diagonalization of A. So when he asks for the diagonalization of A, ironically, he's asking us to do the same exact thing that we did all of these times. He's asking us to do the same thing again, except he just wants us to write, like basically on this problem, he wants us to stop here. So this is the diagonalization of MN. He wants us to stop there. So we can go through the same process and say determinant of A minus lambda I equals uh, determinant of 1 minus lambda 3, 3, 1 minus lambda. So that's going to equal 1 minus lambda, 1 minus lambda, minus 9 is going to equal 0 by the properties we talked about earlier. So there's going to be 1 minus lambda is minus 2 lambda plus lambda squared minus 9. I'm going to say, yeah, equals 0. So that's going to be lambda squared minus 2 lambda minus 8 equals 0. So I think I can factor this one. So that's going to be what? 2, yeah, minus 4 and plus 2 lambda lambda, right? So that means that lambda 1 equals negative 2 and lambda 2 equals positive 4. So now I can take this same matrix and we know that X is in the null space of A minus lambda naught, as we discussed earlier. I'll copy this early so I don't forget any negative signs this time. So there's going to be 1 minus negative 2. So it's going to be 3. And 1 minus negative 2 is 3. It's going to be 1 minus 4. That's negative 3, right? So now we can do our row operations. We know that the bottom one is going to just give us a empty row. So if we subtract that row from the top one. Right? So now we have 3x1 equals negative 3x2. So x1 equals negative x2. So x equals, if x2 equals 1, x1 equals negative 1. So then we can do the same thing here and zero out a row by adding them together this time. So it'd be 3, negative 3. So now we have negative 3x1 equals negative 3x2. So x1 equals x2. So x2 equals 1, 1. So to put it all nice and pretty, this eigenspace negative 2 is spanned by negative 1, 1. And this eigenspace of 4 is spanned by 1, 1. If they ask for eigenvectors and eigenvalues, if you put it in this form, then you will get 100% of the credit. Depending on whatever form he wants it in, this is like the final form, so you always get all the credit for that. So what we can do is we can build our things. So P, what is P going to equal? Yep, that is correct. And what about lambda? That is correct. Got that. So now all I have to do is take P inverse, which I bet you this time I'm going to remember. And we're going to see. I'll forget it by the time we get there. So we're going to be negative 1 minus 1. And we have to swap those. So it's going to be 1, negative 1. Then we have to make this negative. Oh, and this makes it easier. No, no, it's still going to be negative 1 half. So it'll be negative 1 half, 1, negative 1, negative 1, negative 1. I wonder if I should start. No, never mind. I was about to say I wonder if I should just start to multiply it and then right away, but then I may be dealing with a lot of fractions. Maybe I'll just write it first. So we'll say A equals negative 1 half, and then we have P, negative 1, 1, 1, 1, and then we have negative 2, 0, 0, 4, and then we have inverse 1, negative 1, negative 1, negative 1. All right. So this one looks slightly different than the one professor had. I believe he just might have used the different, might have multiplied everything into something. I don't know. But his looks a lot more ugly than mine. And if you look at it, like he must have chosen, like I chose for this one, he kept the threes. Let's look like what he did there. He kept these threes. And I chose my x1 to be positive, and he chose his x1, excuse me, I chose my x2 to be positive. He chose his x2 to be negative. So it is the same, except he kept more numbers and he chose the opposite number to be negative on here. But other than that, it's the exact same. And if you look here, this one is flopped as well. Like because he chose his x2 to be negative, I have 3 negatives and 1 positive, and he has 3 positives and 1 negative. Um, and he must have named his eigenvalue differently as well. I call my eigenvalue, I call my lambda 1, negative 2. He called his lambda 1, 4. So he just used different numbers, but as you can see, it's like, things moved around, but it's the same things. But this is what he wants, so oh yeah, same answer. So it's the same thing. Like if I chose the exact eigenvalues he did and everything else, everything would be swapped around and all, and my math would be slightly different enough. And if I didn't simplify these, I don't know, I don't remember what process he used. He used a different, he might have used a different, just like how he used for problem 5, he used the XC1, lambda 1V, whatever he used, this is a different process. But as you can see, the numbers are the same. Like we end up getting the same numbers. Like if he had the threes and everything, but it's just his process just brought it to a different place. But it'll give you the same answer. As long as your algebra is right, it will give you the same answer. I guess it's possible like you can make a typo somewhere or something, but the process is correct. And all we have to do here is, so he wants the diagonalization. So basically, we know from earlier that these are the eigenvectors. These are the vectors. So what we can do is we can check and see if that's orthogonal. So x1 dot x2 is just going to be, these vectors vectored to each other. So this would be -1 plus 1, that's 0. So that means that these vectors span the space, and they're orthogonal vectors that span the space. So how are they pointing? How are these vectors point? There's like a right angle between them because they're orthogonal to each other. They might be pointing some crazy way. I'm not good with that part, but they have a right angle between them. So now you're saying recall eigenvectors of a symmetric matrix are orthogonal, which we just showed. So they will form an orthogonal basis. If you want them to be orthonormal, so basically what he's saying is we want to find a basis that's going to all show a length of 1. So all I have to do is I'll copy this down for convenience. I'll just divide them up. So this is my first one. This is my second one. And we'll call this P1. We'll call this P2. So if I want Q1, that's going to be P1 over the magnitude of P1. So that's going to be 1 over the square root of 1 squared plus 1 squared, -1, 1. So that's going to be 1 over square root of 2, -1, 1. And by the same token, Q2, which we'll call the orthonormal basis, is orthogonal, but it also has a length of 1. It's going to be P2 over the magnitude of P2. And to do this one out fully this time, this will be 1, 1 over the magnitude of b square root of 1 squared plus 1 squared. So this is going to be 1, 1 over square root of 2. So this will be the same thing, 1 over square root of 2, 1, 1. And if you look at his answer sheet, that's how he got those answers. Again, he's a math person, so they gotta be extra about it. So he actually divided that up in there. 1 over square root of 2 and 1 over square root of 2 and 1 over square root of 2. I'm not a math person, so I try to do as little math as possible, I guess. Uh, I multiply a. I'm not sure about that. We could try it out and see. See. So you're saying multiply a, and I forgot what a was. It's 8, 1, 3, 3, 1. Yeah, it looks like it will. 3, 1. So I'll try. Well, it definitely won't do it with this one because that's all positive. But yeah. So I guess it doesn't work with a. I guess you're just saying that it spans the space and its length of 1. But this looks like it. Notice this will actually still end up with a matrix 2 by 2. Oh, will give us a vector. It'll give us a 2 by 1. So this will be -1 over square root of 2 minus 3 over square root of 2. And this will be uh, -3 over square root of 2 minus uh, 1 over square root of 2. I think I did that right. So this will be -4 over square root of 2 and -4 over square root of 2. So I'm not really sure what that means. I don't think we've ever had to multiply by the matrix itself, but that's what it does though. Yeah, yeah. So in other words, This like A is R2. A is an R2. So what this means is these two vectors, P, these two vectors span the whole space. So let's say this R2 space was our XY matrix, XY plane. And I don't know what these vectors are, but let's just say that one is here and one is there. What this means is that these two vectors, P1 plus P2, you can draw any vector in this whole space by adding a little bit of each one because they're orthogonal. It spans the whole space. And Q simply means we have these same vectors, but now they're one long. So this one is P. Exactly. If you want to show that they're orthogonal, it'll be Q1 dot product Q2. So that will be, where are they at? Here. So this will be uh, these multiplied together. So that'll be -1 over 2 plus these multiplied together, 1 over 2, that equals 0. So we know they're going to equal 0 because the p's was already orthogonal. Like these was already orthogonal, so we did that here. So we already know they're going to be orthogonal. It's just that now they're orthogonal and they equal 1. So let's say, like, let's do that. Let's get the magnitude of any one of these. This will be the square root. So I got the magnitude of this. This would be -1 over square root of 2 squared. So that's 1 over 2. Actually, hold up, I'm going too fast. This would be square root of 1 over square root of 2 squared, 1 over 2, and plus 1 over square root of 2 squared, 1 over 2. So that equals the square root of 1 over the square root of 1 half plus 1 half, 1 equals 1. So that means the magnitude of this thing, Q, is 1. So that makes it orthonormal. It points in the same direction as P1, but Q1 is actually one length long. That's the only difference. And the same thing with Q2, it points in the same direction as P. They point in the same exact direction because 1, 1 points in the same direction as 1, like 1 anything. 3, 3, 2, 2 is all going to point in the same direction. But they're long, the magnitude of those are, like the magnitude of this is what? 1 squared plus 1 squared. What? Square root of 8? And not the length of that is not 1. The only difference is the length of these vectors is 1, and they're at a right angle to each other. So they span the space perfectly at the basis. So that's all that is. So, any questions on anything we did at all before we close up? Awesome. You're welcome. Thanks for joining. And hopefully everybody does well on the exam. What about you, Kelvin? Any questions? All right. Thank y'all for joining. I'll see y'all next time around. Bye-bye. Thanks.